So welcome everyone. So as you know, I'm Lorenzo Maggi from Nokia Labs. Colleagues of many of you. Again, apologies for not being there with you. So I feel that I don't know most of the people that are attending. So well, feel free to reach out or ask any question. So what I'm going to do is a kind of a continuation of what I presented 1 year ago, actually almost exactly 1 year ago. It was at Links Avenue Italy back then, where I was presenting to a fair number of people, and I remember basically the chapter 1 of this very nice book by Che and Viswanath, Fundamentals of Wireless Communication. It's not so recent, given all the advances that there have been in wireless communication. But as you know, there's a state-of-the-art for academics, and then the real networks, and actually the real network standards evolve at a longer time scale. So I feel that this book is still pretty much up to date for what's happening right now in 5G, for example. So there are many concepts that were not actually that seemed very futuristic back then, and then that are now actually part of the standard. So I think it's still a very good book. To the best of my knowledge, which is still limited, by the way. So what I'm going to do is to wait a second. Is there a pointer? Yes. So what I'm going to do is to refresh, let's say, the memory. I'm not even sure that if the intersection of the audience of today and the audience of 1 year ago is non-null. But in any case, I will tell you more or less what we said last time, and then add on top a few things. So very briefly, last time basically we discussed about the communication channel. So basically everything that happens between the antenna that transmits information to our mobile phone, and actually both ways. And today we're rather discussing on techniques to basically fool the channel in some sense, and techniques to actually transmit information through this channel. So last time we only talked about the channel, so whatever happens between the transmitter antenna and the receiver antenna. And we went through actually many, surprising many. When I look back at the presentation, I said, wow, it was super dense. I think too dense. So we went through what channel means, what fade-in means, and then many other things like coherence time, Doppler spread, delay spread, intersymbol interference. So we went really from first principle, like transmit a sinusoid and see what happens. To go through indeed concepts like Doppler shifts, which is basically so you transmit a sinusoid at a certain frequency, and actually the transmitter, since it's actually moving in the space, perceives a different frequency, which is different whether it's actually going further away or approaching the antenna. So, and then, okay, I will not go through all details, of course, but just the main one. So what is fading here? So fading is a direct consequence of what I just said, of the fact that there is a sinusoid that is being sent, there is someone that is moving, and there are also obstacles. And the combination of these three things makes so that actually the amplitude of the signal that is received by the mobile phone is actually fluctuating. So so this frequency shift translates into an amplitude shift. Okay, because basically, if you think about it just a second, so if you sum up two sinusoids as slightly different frequencies, then you have what is called this fading. So it's basically like when two guitar players are playing the same note, and which is slightly discordant, and you hear something like wow, 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 right? And this is basically the same effect, except that we're not hearing it, but we're feeling it through our connection. So, well, we said many things, and we basically went from transmitting a sinusoid over the air to a much more, let's say, convenient model, which is baseband. What does it mean, baseband? Basically, whatever happens over the air is over a certain frequency, right? The baseband is around frequency 0. And why? Well, because it's more convenient to treat baseband signals rather than, let's say, over-the-air signals. And then not only this thing, well, and this basically, this baseband thing is, well, its direct consequence is that you will see complex symbols, complex information. The fact that the information symbols that we send are complex are due to the fact that when you transmit at high frequency, you can transmit over sinus and cosinus. Okay, so whatever goes on the cosinus is the real part of of your complex number, and whatever you transmit on the sinusoid is on the imaginary part. So basically, whenever you hear me saying you transmit a complex symbol, and you say why complex, it's complex because actually there's something, there's a whole reasoning behind that says, well, whatever is on the real part goes on the cosinus that is sent over the air. Whatever is on the imaginary part, it goes over actually the minus sinus. Okay. Well, blah blah blah, and then okay. So this is maybe one of the last things that I wanted to tell you about last time. So, and from which we will resume today. So all in all, so we went from frequency over the air, sinusoid over the air, to a complex symbol baseband model. We still had there was still the problem that the signal was continuous in time. We like discrete things. PCs generally like discrete things, so we discretize it, and then at the end of basically 30 pages of this book, you get to this very nice formula. It tells, okay, suppose that time is discrete and goes like m equal to 0, 1, 2, 3, and so on. Well, whatever you receive at index m can be seen as a weighted sum of whatever you have transmitted x, where the weights are this h, which is called the channel impulse response. Okay, so basically you transmit x, and then you receive y, which is not exactly a replica. It's basically indeed it's a convolution between what you have transmitted and the channel response. And actually, this is, I mean, magical. If you think about how many steps we went through, it's magical to get to such a neat formula where everything is complex. So what you transmit is a complex number. What you the complex the channel response is a complex signal, and whatever you receive is still a complex number. Well, what's is still not super convenient here is that indeed there's no direct correspondence between what you've sent and what you've received. Ideally, we would like to have y of m equal to something times x of m. We try to understand what this something is, and then we remove it, we divide by it, and then we retrieve x. Okay, this is our dream. Okay, and I will tell you how to achieve this dream. Okay, have very grounded dreams. So okay, let's skip all this. And let's get to what we're supposed to talk about today. So in the if you see the note online about this this talk, you will see that I was promising to talk about diversity first and then OFDM if time permits. I actually decided to swap because I feel that, well, makes a better story, and also FDM is really important. Also 5G of OFDM is everywhere. So I think it's a good thing to have a grasp on. So this is basically a recap of what I just said. So okay, there's a typo here, it's easy. But what we want to do here is to overcome this last hurdle of intersymbol interference. Intersymbol interference is what I just said. The fact that the received symbol is actually a weighted combination of what you have sent over time, and it's not a direct, it's not basically a scalar multiplication or complex multiplication of what you have transmitted. So ideally, we want to go from here to here, where I actually put on purpose h tilde, because h tilde does not need to be equal to h, has to be something, okay, that multiplies your symbol. And that's something we will see what actually ends up being. And the benefit is that, well, the receiver is going to be definitely simpler. So in order to get, so you will see that OFDM is basically just one diagram. But in order to get there, one has to have a grasp on some basic, let's say, concepts. I'm pretty sure that at least 80% of you know of this, but okay, for the rest, remaining 20%, let's go over it. So first of all, what is convolution? We just saw it. It's indeed a weighted combination of the input signal, where the weights are what we call the impulse response. So basically, in order to get y of 0, where y is the convolution of the h and x, you basically, visually speaking, you flip h, you multiply element-wise, and then you sum. Okay, and then in order to get y of 1, then you shift by 1 this h vector, and you do the same thing, and then you flip, and then you shift, you shift, you shift. Okay. What is now circular convolution? And you will see that this is basically what we need. So the channel gives us for free, let's say, the convolution. What we would like to have is the circular convolution. You will understand why later on. So basically, circular convolution, so this is the formula, but intuitively, so in order to have circular convolution, you have to have two signals, discrete signals of the same length. Okay, and if they are not, just fill one of the two with zeros. Okay, and then what you do is, well, instead of let's say flipping H like this, you flip it and then you wrap it around. Okay, so you basically flip it and wrap it around. Okay, so this is why it's called circular. So if you wrap it around, you have H0, and then you wrap H1 at the bottom, and then you go backwards. Okay, and then if you do the same thing, so you multiply element wise and then you sum, you get Y0. Okay, you see the difference between the two. And then in order to get Y1, basically you shift it by 1. So H0 goes here, here it goes H3, here it goes H2, and H1 circularly goes to the first position, and so on. Okay. And why is this circular convolution important for us? Because of this property. But in order to go to this property, I have to introduce this other two concepts: discrete Fourier transform and its inverse. Basically, so let's assume that you know what the Fourier transform is. Discrete Fourier transform is, without any surprise, is discrete analogous. So basically, when you have actually, let's start from the inverse discrete Fourier transform, which is maybe easier to understand. So let's suppose that we have this calligraphic F signal. In order to get to F, you apply this IDFT in the inverse discrete Fourier transform that works as follows. Basically, Fi are seen as the basically coefficients in frequency. So Fi is the coefficient assigned to a frequency that is multiple of I. And basically, what you do is you sum this frequency of this, let's say, sinusoid and cosinusoid of frequency which is proportional to I, where the weights are this F. Okay, so you have to basically imagine several sine and cos of different frequencies that you sum with specific weights. Basically, the discrete Fourier transform is basically the inverse. In order to get these weights, you basically project the signal F onto a certain frequency. And if you're, let's say, if you remember what Fourier transform is, basically this is analogous in the sense that frequencies are only allowed to be an integer multiple of 1 over n, where when n is the length of the signal. So basically, instead of having a discrete, continuous signal, you have a discrete signal. And instead of having a discrete Fourier transform, you have a discrete Fourier transform, which has exactly n points, which can be thought as a frequency that are multiple of a specific frequency, which is 1 over n. Okay. Well, why am I saying all that? Because we do like this property. We do like the property that the DFT of the circular convolution of two signals is the product of the two DFTs. Okay, I just put here the proof because I just wanted to prove by myself, and then I leave it there. Well, let's go through it. Although they're just basically just basic, fairly basic steps. Okay, But what we do like is that basically the DFT transforms something that we have almost for free, almost, because actually what we have in practice is a convolution, okay, into something that we like, is this product. Why? So let's try to imagine. Let's try to put in practice this property onto the wireless channel that we saw before. So imagine that we do something like that. Well, we have something to transmit, that is this calligraphic X. Before it was X, now it's calligraphic X. It's basically the same thing. I called it calligraphic X because one has to think as if it were in frequency, as if it were the DFT of something, okay? Which is in the end. So let's say that we have n symbol transmit. Actually, you have, let's say, infinite symbol transmit. But let's say that you chop your stream of symbols onto a batch of n symbols, and then what you do is go from serial to parallel, and then you apply IDFT. Why serial to parallel? Because the IDFT, so in order to get each coefficient, or each output coefficient of the IDFT, you have to process all the inputs at once. The IDFT is basically a matrix multiplication. So in order to get the first output, we already have to have all the inputs. Okay. Well, you do this, and then you transmit whatever comes out of the IDFT. These are the effective symbols that you transmit. Then there's a channel that does its stuff, and the stuff is basically a convolution between the channel response and what you have transmitted. And then you do basically the reverse. So from serial to parallel, and then DFT, and then you decode symbol. What we would like is that these output symbols are basically the input signals times something, okay, and not the convolution of the channel response. So is it true? No, almost. Why almost? Because if you do the DFT of H convolution X, you don't get exactly DFT of H times DFT of X, because we should basically, because there's still a convolution. We don't like convolution. We like circular convolution. Okay, so if there were a circular convolution here, well, we would be done, because then the DFT of what you receive is indeed the DFT of H, so basically a number, times the DFT of X, which is calligraphic X, which is what you have transmitted. So you would get indeed a relation that we like. So from convolution to circular convolution, actually it's a very simple trick. So basically, you basically fool the receiver. You let the receiver see something that has not really happened, almost. So what you do, instead of, well, you do as we said for the first two blocks. So you have symbol to transmit serial to parallel IDFT, and then instead of transmitting the IDFT, well, you pre-attach symbols of the last L symbols of this sequence. Okay, in a, let's say, circular way. Okay, you take the last L symbols of this sequence, and then you attach it as a suffix here. Okay, and then you let the channel do its stuff. So what happens? It happens that basically the convolution makes in such a way that x0, well, what you decode as what you receive as y0 is actually the weighted sum of what, of x0, xn minus 1, xn minus 2, and so on. And so basically, you see that it's almost what we have here. Okay, so x0, x3, x2, x1. Here we have x0, x minus 1, x and minus 2, and so on. Where I forgot to say, L is actually the length of the channel, the spread of the channel. We still have to do something. Well, the first L minus, the first L symbols are like basically garbage for us because they bring no information, and actually they're not exactly a circular convolution anymore. So we remove the first L received symbols, and the effect of it is that what you see here is indeed the circular convolution between X and H. So I hope I was not so much unclear. So basically, you pre-attach the last L symbols in order to basically let the receiver feel that there is a circular convolution, because indeed the H channel response is basically acting, is as if the channel response were acting in circular way on what you have transmitted. Okay, so all in all, via this suffix, no, suffix is well, I forgot the term, but by pre-attaching the last L symbols and removing the first received symbol, what the receiver sees is indeed a circular convolution. So what we liked at the beginning, well, what was our target, is actually achieved. So what you decode here at the end of this whole chain is indeed what you have transmitted at the same slot times something, where this something is actually the DFT of H, well, the nth element of the DFT of H. Okay. So it basically, well, plus noise. Here I omitted noise for simplicity, but the same thing that can be said through noise. Well, basically you will have plus a DFT of the noise, but DFT of the noise is still noise. Okay. So, and basically this we achieved what we wanted. Then I also want to tell you one more thing about this OFDM. So if you search for OFDM over the web, most of the times you encounter this very figure, and where they talk about basically the spectrum of an OFDM signal. So it may be a little bit confusing, because this spectrum is the spectrum of a continuous time signal, while here we didn't talk about continuous time signal at all. Everything actually happens in baseband and in discrete time. So the two things, at least to me, are always confusing. So this is why I wanted to just at least give my personal view on this. So this is basically what you find on the web is basically the spectrum of an equivalent signal that is continuous time, and that if you basically sample every t, where t is to be agreed upon, is basically the discrete signal that you have that I put in this slide. And basically, well, I don't want to delve into too much in this, but what is done is in order to, well, in your real life, and still, so this digital model is still a model. What you do in your life in order to send it over the air, you have to switch to an analog signal, and the equivalent analog signal looks like this, where basically this can be thought as a sine, cos sine at frequency, which is multiple of this delta. So basically, what you end up having is a symbol xi that modulates a subcarrier, what is called subcarrier, at a frequency that is proportional to I, to the coordinate of the symbol that you're transmitting. So this is just a small aparte in order to tell you that there are basically two ways to explain OFDM: a continuous time and a discrete time. The two are not, I mean, the two go well together, but I just feel that the discrete time is easier to understand. So this is why basically I went through the discrete time. Okay, so this is the end of the first part, where basically we talked about how to get to a very neat channel model. We started from sending sinusoid over the air, and then we ended up having y equal h times x. Okay, super simple. Well, it was painful to go through all these steps, but you can basically up to now, up to here, you can basically forget all about all what I said up to now, and just think of the channel as a very let's say straightforward thing that takes an input and multiplies by a complex number, adds noise, and this is what you get at the receiver. Okay. If you have questions over the first part, please. Otherwise, I would go to the, let's say, part 3 of the whole story. Okay. No questions. So I hope you're still with me. This is part 3, receiver diversity. So basically, up to now, so we have talked about this communication channel, whatever happens between the transmitting antenna and your mobile phone. Then we talked about OFDM, how to further simplify this model, and then we got to this very neat equation. Now let's start talking about how to actually transmit information. Well, we didn't really talk about how to transmit information efficiently. We just said that there is something to be transmitted, okay, and something that is received. But then this something has to convey information, what you want to transmit from point A to point B. And there are tons of different ways to do that, okay? So the simplest way is just to transmit, well, to encode. So encode whatever you have to transmit into bits, go from bits to complex symbols, which we didn't talk about, but let's assume that there is a way that basically transforms bits 0 and 1s into complex symbols to be transmitted. Okay, and then you just transmit them one by one. Okay, well, it works, but it's not so efficient. Well, one of the main problems is that, so this H is something that varies over time, that can be, that this complex is a complex number that varies over time and can be very small in amplitude or very big in amplitude. But it's essentially a random variable, complex variable that is usually well, in textbooks, then it's not really so in real life, but in textbook, it's usually modeled as a circular Gaussian variable. The circular Gaussian variable is basically a Gaussian variable in the complex space where real part and imaginary part are both Gaussian, and they're basically independent. Okay. And with each one has a variance of 1/2, such that the overall variance is 1. Okay, and zero mean. Okay. So the problem is that if h is small, so is the amplitude of h is small, then, well, the noise will prevail and x cannot be retrieved at the receiver, as simple as that. So option 2, well, you can transmit the same symbol x over multiple slot or antennas, you will see, but let's say over multiple, let's say channels. So such that the same X experiences different channel conditions. Sometimes it's good, sometimes it's bad, but the probability that all of them are bad, if you transmit them over many slots, is very small, right? So basically, and this is the main concept around diversity. So you transmit the same thing over multiple, let's say, channels. The probability that all channels are bad is very small. So you're happy because the probability of a bad reception is small. On the other hand, you're not so happy because you're using the channel multiple times to say the same thing, right? So this slows down the transmission. So so indeed, this is the simplest and well, the most naive way to achieve diversity. And we will see that there are actually principled and better ways to achieve diversity with a better trade-off between redundancy and error probability. So basically, you transmit more symbols over time, and at the same time, you basically manage to achieve diversity. So let's start from, let me check the time. Yeah, as usual, it's taken me longer than expected, but okay. Just kill me in 20 minutes and it's fine. So if you transmit one symbol, symbols one by one, and let's just simplify our life. Let's just think that symbols are plus or minus a, plus or minus 1, let's say. Okay, so they're not complex, they're real. It's okay. It's the simplest, it's called a QPSK. It's the simplest modulation scheme that one can think of. Well, let's think of what the channel does. Well, you have this h, which is a complex number. You multiply it by plus or minus a, let's say plus or minus 1, and then you add noise, and then you get what you get. So this y, okay? Then in order to decode what has been transmitted, well, the receiver knows that there were just two options, either plus a or minus a. Know that the realm of options is just 2. So what it can do, well, it should do, it's actually maximum likelihood best option, is to basically project whatever has been received onto the channel, and then decide whether it was sent plus or minus 1, say, based just on the sign of what you get on the real part of this projection. So basically, you project onto h. Well, actually, normalized version of h such that the norm is equal to 1, and then you take the real part. If it's positive, then you say you guess it was a. Otherwise, you guess it was minus a. Okay. And then let's compute the error. So this is the simplest thing you can possibly do. So let's compute this error probability. So error probability, what is error probability? It's probability that you decode, you don't decode the symbol that has been actually transmitted. Either way, whether it's transmitted plus A, you decode minus A, or transmitted minus A, you decode A. So let's say that you know H, and H is given, which is not true, but let's start with that. So the probability that you decode the wrong thing is basically that the probability that the noise, so the only problem here is noise, because if there's noise, you always decode well, right? So the probability of mistake is the probability of that the noise makes you flip on the other direction. So you transmit H times 1, and then the noise makes you flip in the other direction. What is this probability? So basically, the noise is a complex number, but the only thing that we're interested is on this line, right? Whatever occurs out of this line is not important to us, because we always project in this line. So the problem is when the projected noise onto this line is such that is so big that this vector points in the other direction. So basically, is the probability that the noise is greater than A times the magnitude of H, right? Let's say that A is 1. So, and then we can call it, so we can sum on the Q function, which is basically the probability that a Gaussian variable, standard Gaussian variable is greater than something, to basically to have, let's say, a neat expression. But then we still have to average over all possible H, because H could be known. I mean, there are ways to estimate the channel, but still H is not at all fixed. So if you average over all H, then you get an expression that is inversely proportional to SNR. And actually, this is not surprising, because basically what is, so 1 over SNR is basically the probability that the channel is so bad such that the overall received signal is smaller than the noise power. So just to say that 1 over SNR is not a surprise. Okay, so it's basically the probability in some sense that the channel is bad. Okay, so how to make this better? The same symbol over multiple slots, over multiple, let's say, channels. So what you receive here is basically a vector, which is x, which is the same times the vector of channels. Okay. And okay, I will spare you the details because we're a bit late, but unsurprisingly, what you get after, well, a fair amount of computations that you can see in the book, is something that is proportional to 1 over SNR to the power of L. And still, this is not surprising, because we said that 1 over SNR is the probability that one channel tap is bad. 1 over SNR to the power L is the probability that all channel coefficients are bad. And of course, I mean, this is much smaller than 1 over SNR. So basically, this we achieved intuitively what we said at the beginning. So when we transmit the same signal, same symbol over multiple channels, the probability of mistake is the probability that everything goes sour. Okay, and Okay, I'm skipping a few details here, but because I want to at least cover everything here. So Alamut scheme. This is another way to achieve diversity, which is much less naive. But if you think of it, I think I mean, it's really genius. It's really super simple and super effective, and indeed is not by chance that it was really picked up almost everywhere. So Alamut scheme was standardized and was actually used already in 3G, I think. So so Alamut scheme works with any number of antennas, but let's start with the simplest case. Let's start and finish also with the simplest case, with 2 transmit antennas and 1 receive antennas. Okay, so antennas is basically whatever we just said is with 1 transmit antennas. If you have 2 transmit antennas, add the transmitter, you can transmit different things on different antennas. Okay, as simple as that. The crux is that different antennas experience different channels if they're sufficiently far apart. So basically, you can achieve diversity over time, but also over antennas. Okay, and antennas here is also called space. Over space means antennas. So whenever you hear space-time, space is actually antennas. Okay. So what you do is something slightly more complicated than the repetition code. Well, actually, you don't transmit whatever you have encoded as complex symbols, but you do another transformation, and the transformation is, let's suppose that you want to transmit these 2 symbols, complex symbols, U1 and U2, and you have 2 slots to do that. Okay, either you say, well, I transmit U1 on antenna 1 and then U2 on antenna 2, but the problem is that whenever H1 is bad, H1 cannot be received. Same thing for H2. Otherwise, you can do something smarter. You say, well, at time 1, what I do, I transmit over both antennas, and at time 2 as well, in such a way that, well, let's not skip to the conclusion. So at time 1, you transmit U1 on antenna 1 and U2 on antenna 2. At time 2, you transmit minus U2 conjugate on antenna 1 and U1 conjugate antenna 2. Well, if you rewrite this and in matricial form, and basically you take out U1 and U2, which is actually what we want to decode, you basically get this equation, matricial equation, where, well, you will figure out that the columns are orthogonal. Okay, so basically what means is that, well, what you receive is basically column 1 times the first thing that you want to transmit, plus the second column times the second thing that you want to transmit. So basically, the receiver what can do, and what should do also, is to to wait for 2 slots. Then it gets Y1 and Y2, and then projects Y1 2 on the first column, and then on the second column. Since they're orthogonal, the other column is basically nulled out, and then and then it decodes in a similar way as we saw before. What is the great advantage is that the U1 is as if the U1 went through to realization of the channels, because you see U1 over H1 and H2. Well, when you take the product, it gets a absolute value to the power 2. So basically, it's as if we had 2 repetition codes on 2 slots, where each symbol sees 2 different realization of the channel. So basically, we achieved what is called diversity degree 2, because each transmitted symbol has seen 2 different realization of the channel. We could have done this to repetition code, but we would have needed twice as slots, right? But here we have transmitted 1 symbol per slot, because we have transmitted 2 symbols over 2 slots on average. So, which is much better than just the repetition code that would have just transmitted 0.5 symbols per slot, right? So this, well, I am not sure whether I still have time. Okay, well, it's maybe 5 minutes. If you wanted to stop here and ask questions, please do. Otherwise, I will tell you what was a natural generalization of all this. If you have questions, we can even stop here. Otherwise, I will go through the last 2 slides.
In the room, we don't have any questions, it seems. And online, there are quite a bunch of people, but I don't see any.
Okay, no problem. So I assume that everyone is sleeping, or so it's very good. So let's go to this space-time codes just to conclude. So space-time codes, which really sounds well, very futuristic at least, is nothing more than a generalization of what I just said. So where information is encoded across time and space. Space is antennas. So time, because you have multiple slots that you can transmit across. And space, because you have at your disposal many antennas. Okay, so you have L antennas and N slots. So, well, repetition code is a sub-case of this, where you transmit these code word. So on slot 1, you transmit plus or minus A on the first antenna. On slot 2, you transmit plus or minus A on the second antenna. And it's basically a particular way to implement this repetition code. You can do it over time, over 1 antenna, or over different antennas across different time slots. Alamute scheme is also a sub-case where basically over the first slot you transmit this over the 2 antennas, and the second slot you can transmit this on 2 antennas. But what if we want to generalize this and you say, well, I have L antennas, I have N slot at my disposal. What can I do in order to minimize the probability of error? Well, so it's a little bit more involved than before, so this is why I'm skipping a lot of details. But all in all, basically what you should do, so all in all, I'm skipping all these details, but this probability of confusing one code word with another one can be bounded by something that has SNR to the power of L at the denominator, just like before. So L is indeed the number of time slots that provide L is the number of antennas that provides diversity. Okay, this we already saw it before. What we have not seen before is this term, basically, which, well, is a bit involved in the sense that these are the eigenvalues of these metrics, which is basically the difference of the 2 code words, okay, times this emission. But basically, the main message is that you achieve diversity here, which is good, but another way to decrease the error probability error is to design these code words that in the repetition code and the Alamute scheme were basically fixed, were by design. But if we can further design them, well, we should design them such that this product of eigenvalues is as big as possible, such that the probability is as small as possible. It turns out that if this, this basically is related to how code word, how far this code word are in space, one of the respect of each other. So basically, what you cannot, well, the farther they are, the less efficiently you're using the space, right? The less you're packing the code words in the space. So, of course, the error probability is decreasing, but on the other hand, you're transmitting at as lower pace because you're transmitting less information, right? So basically, there's a trade-off between what is called coding gain and the transmit rate, and which leads to all the MIMO communication that is the basis of, let's say, 5G and even 4G. But okay, well, I want just to conclude here. So as a recap, well, we went from communication channel that is whatever happens from the antenna, transmit antenna to the receive antenna on your mobile, to ways to further simplify this communication channel, and basically to get to a very simple formula of the kind y equal hx plus n, where h is the whatever is the effect of the channel, x is what you transmitted, and n is some noise. And then what we have discussed in the last part is how to efficiently transmit actual information through this communication channel, whatever it is. Of course, this is not the end of the story. It's just the beginning, to be honest. But yeah, I feel that, I mean, I think it's already, these three parts are already a very good, let's say, basis to understand, let's say, a wireless communication paper nowadays. I mean, for those of you who are interested, I really prompt you to have a look at this book from Che. But of course, there are many others that are more recent. What I have in my bookshelf is MIMO Communication by Robert Heath, which starts with some more prerequisites, but I feel this is really, let's say, it covers many more topics around MIMO communication. MIMO is basically the communication where you have multiple antennas at the transmitter and multiple transmit antennas also the receiver. Here we just saw a very simple example of that. And well, that's it. If you have any questions, please ask. Otherwise, I hope we can see each other anytime soon.
Thank you, Lorenzo.
Welcome.
So do we have questions here in the room? Yes, we have one question by Francois.
Yes, thank you. It was a very nice lecture, quite clear. First one, additional type of question that comes to one's mind is about, I mean, a connection with information theory and the Shannon capacity, things like that. So for all these schemes, I mean, these are, I mean, you here in these chapters you describe, I mean, things which are quite transparent in terms of how you decide to encode with this and how you decode, but these things are certainly linked to information theoretic limitations. And so, could you comment a little bit on how far is this from the Shannon formulas for the
Yeah.
For the I mean, this type of channels.
Yeah, absolutely. So yeah, Shannon theory. So if you want, in March 2024, I can I can cover that chapter on information theory. So it's actually a different paradigm. So here we only talked about, actually very briefly, about this probability of error. Okay, right? So which are always positive, right? Shannon theory is about making this probability of error tend to 0. And basically the main philosophy is Shannon theory tells you, well, how fast can I, well, how fast indeed, about how fast we talked about the transmission rate, right? How many symbols were transmitting over time, and we said, well, here I'm transmitting 1 symbol over slot, there I'm transmitting one over 2 symbols over slot. Shannon is actually its rate is actually on bit per second, right? Because the symbol is after the encoding bits, right? But it's I mean, it's clearly linked. So Shannon theory tells you, given a channel is this whatever happens between receiver and transmitter, what is the highest rate in terms of bit per symbol per hertz, but okay. But the highest speed of transmission that I can go, such that if I have an infinite time to encode this into some complex symbol, the probability of error at the receiver goes to 0. And actually this infinite time is, let's say, it's an artifact, it's mathematical artifact, because no one has infinite time, but it already gives you, let's say, the boundaries of what cannot be achieved. You basically, thanks to the Shannon theory, you already know that if you're transmitting at a certain speed given a channel, nothing good can come out of it. This also does not mean that if you transmit at the speed that is lower than the Shannon limit, you will have 0 probability of error, because this 0 probability of error is if you have infinite amount of time to transmit something. And usually you don't have an infinite amount of time, you don't even have many seconds to transmit. So you basically, ideally, you want to buffer your information for, and you have a huge vector information to be sent before being decoded. Usually you have delay requirements which are very stringent, so you can only do it for basically some milliseconds. But basically, Shannon theory relates to this. So we only talked about probability of error. Shannon theory tells you how fast you can transmit things such that this probability of error can go to 0 pretty fast in some sense. And this is I mean, this is, yeah, definitely super interesting. It's actually, Shannon theory, I think that it can be seen as putting boundaries to what you can do. I mean, over the Shannon formula, nothing good can come out of it. Below the Shannon rate, one should find actually practical ways to transmit communication such that the probability of error is sufficiently small. So it's another paradigm, but it's definitely very interesting. And yeah, maybe in 1 year I can talk about it.
So any other questions here or online? I think no. So thank you once again. I personally liked a lot your OFDM explication and presentation. So thank you for that.
Okay.
So we wrap
Thanks
it up.
to you.
Thank you.
Thanks to you. Thanks to you for the invitation. Bye.